Okay, folks, I want to look at the following. We are told, when we look at this equation written this way, where that's not a W, by the way, that's an omega. I just did not draw this very well. That's the omega. That C is the phase shift. If I just write properly, phase shift, that's a T. I'm going to have to erase that. Okay, phase shift. There we go. It's better. Great. And then if I factor omega, what I have is the following. So I factor omega. And then, when written in this form, C over omega is called the horizontal shift. Fantastic. Now I want to show you how else you can think of this. How else can this make sense, given what you know already? So now hang on for a second. So I'm going to call the phase shift the natural period. Okay, you'll see what I mean by that in a second. Maybe I should call it natural period value. Ooh, I like that better. Much better. Well, the horizontal shift, I'm going to call the modified period value. Now I'm making these words up. So if you try to look this up somewhere, well, you're not going to find anything because I've just made this stuff up. But I want to connect it to something you already know. So I'm calling the phase shift, C, the way it's written right here, the way you see it, the natural period value. Well, I'm calling C over omega the modified period value. Okay, let's see how this makes sense. Okay, so I'm going to write the following. Y equals sine of theta. And it has the same meaning it always has, which means that if I draw a unit circle, oh, you know, it's a unit circle. That's a -1. Boy, that's lousy. I'm going to draw a circle right here. I'm not going to draw a full circle. Okay, I'm going to draw a full circle. And this is the unit circle. And this is theta, the angle formed in standard form. That point on the circle itself is x comma y. And of course, sine theta is that y. In other words, what we have here is cosine theta, sine theta right here. And sine theta is equal to y. Great. Keep that thought. To make this as intuitive as possible, I'm now going to consider the following. This is going to be another circle. But it's not going to be like the circle above. No, this is the face of a clock. So it's got 12 o'clock, 1 o'clock somewhere here, 2 o'clock somewhere here, 3 o'clock somewhere here. And that's, it's the face of a circle. I'm not going to continue. Okay? So that's what that is. And to make my connection to this above circle as easy as possible, this is a unit circle. This is what I'm going to draw is from the center of this circle to the edge. Right here, this is the minute hand. So that line is the minute hand of a clock. Oh, and to make life really simple, I'm going to make it 1 unit. 1 what? Let's just make it 1 inch. It could be 1 foot. That would have been one heck of a clock. But I'll just make it 1 inch right now. Just again, make my life simple. Now you'll notice I call this theta, but instead I'm going to call this angle or something like that. I'm going to call an angle I form. I'll draw it just in this format for a moment as x. Not necessarily in standard position, by the way. I just drew this right now in standard position, but you'll see in a second I'm going to alter that. But clearly what's happening is x is time in minutes. So what I have here is theta, but theta is an angle being formed in standard position, like so. And this is x is time in minutes. Okay? All right. So keep that thought for a second. Now, what I want to do next is just remind you of something. Suppose I'm going from radians to degrees, and we know that pi radians is equal to 180 degrees. And we've already done a few changes in units. You know, if I want to go from 30 degrees to radians, so I know that what I have to do is multiply this by 180 degrees, pi radians. And of course, if I do this, the degrees units cancel, and I'm left with pi over 6 radians, right? So this is your standard way of changing units. In this case, I changed from degrees to radians. Now, keeping that in mind, if I want to go connect this measurement, which is in minutes, the hand of a clock, versus degree angle of a unit circle, I know that similarly 30 minutes is equal to pi radians. And I can use this to convert from, let's say, minutes to radians. So if I want to go from minutes to radians, what I have to do is the following. I just, let's say that I have x minutes times pi radians divided by 30 minutes. I cancel, and what I have is again degrees, but in radians. So really this is what this is doing right now. I'm changing from x minutes to theta radians. So I purposely changed the variable so you can see this transition taking place very clearly. All textbooks, all explanations never do this because they're assuming you can alter and change the meaning in your mind and they show one but not the other. But I want to make the meaning of all this very clear, so I'm using two different variables to do this. Okay, so let's continue. I want to also emphasize something. When we define the sine function, it was in degrees of a unit circle. Now, we can also expand this so it's not a unit circle, but really, I like to think of it as the sine function is defined on the unit circle. We can use a circle that's not a unit circle and still come up with a value, but notice we have to divide by r. We have to do some things. So really, when we divide by r, for example, if it's not a unit circle, the purpose of dividing by r is to get back to the unit circle. So I'm going to say right now the sine function is defined on the unit circle. Okay, so let's continue with that idea. But I'm going to go further. Theta is the angle that, as we've defined before. It could be in degrees, it could be in radians. Right now, I'm just going to stick to radians to make my life very simple. But I'm going to do the following. The sine function can only accept angles. This is going to be very important. That's all it will accept. it'll only accept an angle in either degrees or radians. Okay, radians being really the preferred way to do this, but that's all it will accept. It won't accept anything else. So next, I have this other situation, which is the clock with a minute hand that's an inch long, again, just to make my life super simple. But x is in minutes. And now if I say, hey, wait a minute, sine function can only accept an angle in degrees or radians, and this is in minutes. How do I overcome that? Well, one thing for certain is that if I take my measurement in minutes, x, right here, and I multiply it by this conversion, I get radians. So one thing I can do is measure it in minutes, but then use this conversion to go into radians. So what I can do next is the following. If I want to use the sine function to find, let's say, the y component only on that unit circle, right here, then I write the following. Y is equal to sine of, then I'll take my conversion factor and multiply it by x minutes. So really what's happening is this. Sine will only accept degrees measurement, let's say degrees or radians. And right here I've taken my variable, which is clearly in minutes, but I convert. So at the end, what I have here, this is equal to theta. So the conversion converts it to theta, which is in degrees, and now the sine function can handle it because that's all it will do. Okay? Now keep that thought for 1 second. So here I've drawn a unit circle, but really it's just that clock again with a 1 inch hand. Again, I've drawn the 1, 2, 3 o'clock, and all I care about is to express the y component as the hand itself moves on this clock face. And this definitely describes, this function right here describes that motion. And x minutes is right here as time elapses. Now suppose that I want to instead start this at the 12 o'clock position. So right now the way this is written, it will start here at the 3 o'clock position, but I want to create a shift and really start at 12 at midnight. So remember, if I take this graph right now, it's x minutes, the sine function normally starts here at the origin, and gosh darn it, there you go, and then it starts doing this movement, right? Boy, this is getting hard right there. But I really want to start at 12 o'clock. But notice 12 o'clock on this face clock, if I started at 3 o'clock, 12 o'clock, that is a 15-minute change. Okay, but if I look at it from the degree of radians, that is pi over 2. That's a change of pi over 2. So in that case, I'm going to get rid of this x right here because I want to start 15 minutes later. So really, what I'm interested in right now is degrees. How much of a degree change is that? Midnight, starting at midnight, is starting at pi over 2 as far as radians are concerned. Okay, great. How does that work? Well, you'll notice I'm starting here at pi over 2. So the equation is the following. Y sine pi over 30 x. Okay, but I'm moving forward, so I need to subtract pi over 2. Let me clean this up a little bit. If you look at your notes, you'll notice that this pi over 2 is called a phase shift. If you go back to what I've said earlier, I've called it the natural period value. So the phase shift I call the natural period value. And well, what does that mean? Well, I've called it the natural period value because you'll notice that this right now is theta, pi over 30 divided by times x is theta. Pi over 2 is, again, in radians. So this is all in radians. And that seems pretty dang natural to me. In other words, natural just means that that's the way I just defined it. So the natural phase okay, so it's just natural, but it's called a phase shift. Okay, so I called it before it just a natural period value, the result of a natural period value. But however you want to think of it, it's just how sine is defined. Okay, fantastic. Well, let's figure out the next part. So you notice what I really wanted to do was start at 12 o'clock on the clock. But what does that translate to? 15 minutes. So now here comes the next part. If I were to factor pi over 30, what happens? So I'm going to factor this. Factor pi over 30. I'm factoring the pi. I'll leave that out. But took out a 30, then I have a 30, so I'm going to put a 30 up here. The 2, haven't factored that out. And when I clean this up, you can always multiply to make sure that I'm getting what I start off with, which is pi over 2 right here. But when I clean this up, voila, 15. Wait a minute, 15 what? You'll notice that x was in minutes. I'm subtracting. I can only subtract things that are alike. This must be 15 minutes as well. Hey, wait, I wanted to start at 12. I started at the 3 o'clock position, but when I start at 12, that is 15 minutes. That's actually this 15 minutes, the ones I want to start with. What about this pi over 30? Well, that's my conversion. So right now, all this here is in minutes. X minus 15 is in minutes. This conversion, pi over 30, allows me to go to theta. Then once I convert it to radians, I can feed it to the sine function, and that will give me my y value. So then this is what I've been calling, when I write in this format, this modified. So this is sort of modified, but the 15 now is really called the horizontal shift. And the way I got there is by doing the following. The horizontal shift, if you look at your notes, is defined as C over omega, where C was the original phase shift, the phase shift. So now if I take, for example, the phase shift, where's my phase shift? Pi over 2. So when I do this operation, the pi's cancel. 30 divided by 2 is 15, and there we have it. That's my horizontal shift. So hopefully this will give you a better sense of what's happening here when we go from horizontal shift to phase shift.